Hi, folks. Happy Thursday. Welcome to Abstract Algebra Midterm Exam Review. We're talking through some of the big ideas in group theory and thinking about how we might structure our studying and structure our knowledge in this course as we are prepared to demonstrate some of the things that we've learned. The first idea is we'll want to be able to use our definitions. A reasonable example of this sort of idea: show that the set of real numbers of the form a plus b times the square root of 2, where a and b are rationals, is a group under addition. Okay, now is a great time. Just pause the video, try it out. What would you check? Okay, for our next type of question, we want to think about being able to provide examples of some specific property. For instance, can you give me an example of a finitely generated group that isn't finite? Or tell me about two groups, different groups, non-isomorphic groups that have the same size. No, seriously, pause the video. Think about it. And I'll confess right here, this is partially an example of a reasonable question to ask, but it's also part of you being able to think through your conjectures or your proofs, to have some examples ready to go to sort of say, okay, I'm claiming this thing is true. Can I think of an example or a non-example, a place where it is or isn't true? Making sure you feel comfortable drawing up specific examples of these funky abstract objects is really part of being able to check your work as you go. Next, let's think about what sorts of computations we're equipped to do now in our abstract algebra land. We do have some computational skills. So for instance, we've spent a lot of time on disjoint cycle decompositions and thinking about permutations. Maybe you want to write down the disjoint cycle decompositions of the elements of the group S4 that correspond to the action of D8, our dihedral group of order 8 on the vertices of a square. We could do different computations, like computing the centralizer and the normalizer of a given subset of a group. Maybe the example I gave here, it's a nice subgroup of a permutation group. Again, pause the video, try it out, do some computations. We'll get the answers to these questions at the end, but not until the end. And a final note, as you think about how you want to demonstrate your knowledge and what knowledge you're prepared to demonstrate, just remember there's this balance, right, between justifying your reasoning completely and communicating concisely. I wish I had a nice, easy way to tell you how to check, oh, have I been sufficiently thorough without being overly verbose? It's a hard problem. It's a really hard problem. So I will just encourage you to keep that balance or that tension sort of in mind. Stop and ask yourself every once in a while, have I explained this as thoroughly as I can? And maybe also stop and ask, have I used more words than necessary here? Can I just call it good? I wish you the best as you continue exploring that tension. Onward then to thinking about the specific content before us. So let's see, where do we start? We start with groups, basic axioms, examples. Our examples sort of flow throughout the first chapter of the text. So we've got dihedral groups. Throwback, you remember we had little acrylic shapes that we flipped around and we counted lots of things. We talked about symmetric groups. Those are permutation groups.
The notation we use for these permutation groups, we say S sub n. It counts or is the group of all permutations on n elements. That group is order n factorial. It's another example of a non-abelian group. Speaking of non-abelian groups, we also have matrix groups. The prototypical example of which is the general linear group, so the set of invertible matrices with entries over some field. Remember, fields might be finite. We've seen some examples of the general linear group over finite fields in a recent homework set, but we also have our favorite fields we know and love, things like the rationals or the reals or the complex numbers. If I was thinking about how I would be prepared for questions about matrix groups, I just want to make sure, just really sort of fundamentals of linear algebra, right? That I'm okay with what does it mean for a matrix to be invertible, basic properties of the determinant, things like that. That's worth spending a few minutes just sort of brushing up on or including in your note sheet. We've studied the quaternion group. That's a different group of order 8 as opposed to the dihedral group of order 8. It was one of our first examples of a group of a similar order but a totally different structure. Last but assuredly not least, we talked about homomorphisms and isomorphisms, as well as group actions. So these sort of, the last of our fundamental building blocks are the ways for us to learn about groups by relating them to other groups or other sets or other structures, right? Ways for us to sort of make connections between different ideas. Now, how do we check something's a homomorphism? Well, we want to make sure that it plays nicely with the operation in the initial group and in the target group. Group actions, similarly, a group acts on a set. Sometimes the group acts on itself. Either way, if it's a group action, we just want this relationship to satisfy whatever it is. However we define this group action, we want it to satisfy that the identity doesn't change the element of the set, and again, that the group action respects the group operation, whether we let H act on X and then let G act on the result of that, or if we take G times H and combine those in the group and then let them act on X, we should get the same thing. All right, so all of that being said, let's take a quick peek at some of the notable vocabulary or key ideas that are sort of lurking within these bigger sections. Definition of the group, we're on it. Cancellation laws, you can multiply by the inverse, woo! We know the idea of order, how many times we have to apply the group operation to an element and itself over and over and over again until we get the identity, or the order of the group, the size of the group. We know how to build a multiplication table or a Cayley table. We understand generators and relations. We can see an example of that in our descriptions for D2N or for Q8 above. Let's see, we know how to talk about permutations using cycle notation. We know how to find the disjoint cycle decomposition. We know the basic principles of a field, right? Everything has an additive identity and, an additive inverse and a multiplicative inverse. We've got some basics on finite fields. Let's see. Oh yeah, general linear groups and special linear groups, right? Whether the determinant is just non-zero or the determinant is specifically asked to be 1. We can do permutation representations of a group action. Oof, that's a little bit more, there's a little bit more going on there, right? But at a surface level, at an intuitive level, that's just the idea that when a group acts on a set, it induces a permutation of the elements of the set. You say, oh, this element of my group takes something in my set and sends it to something else in my set. That's a permutation. Don't worry about the details or the mechanics on that. Just remember that idea that we can permute the elements of a set according to properties of our group, and maybe that's a way for us to build some kind of isomorphism or some kind of homomorphism. We can determine if an action is trivial, right? It doesn't change anything. We can determine if an action is faithful, that is, distinct elements induce distinct actions. We can look at the kernel or the image of a homomorphism, or even the kernel of a group action, right? Everything that gets sent to the identity. Conjugation, we love conjugation. We do this all the time. G inverse. Just sandwich your element or your set or whatever with an element on one side and its inverse on the other side. Let's see. We've got the idea of orbit, right? Start with one element in your set and let the group act on that and send that element somewhere else, somewhere else, somewhere else, somewhere else. What are all the things that are in the same orbit? This is kind of a coset idea, right? We can partition our group according to the orbits of a specific action. We also first encountered Lagrange's theorem in here, the idea that the order of an element divides the order of the group. And we talked briefly about roots of unity. It's not a big deal. It's whatever. All right, onward and upward. Now that we've got all these building blocks, what are we going to do with them? Oh, that's right. We're going to think about subgroups. A subgroup is just a group inside a group, all right? It has to satisfy all the same axioms as a group does, but because we're starting with a set of elements that's already contained in a group, we don't have to check as many things, right? So at a fundamental level, it's about closure, containing inverses, and those are the things we check. We proved the subgroup criterion, which gave us kind of a streamlined way to get all of that with one quick check involving XY inverse for an arbitrary X and Y in our subgroup. Underlying that, though, you got to start with just making sure it's non-empty. Got to be non-empty. Some of our fun and interesting examples of subgroups include centralizers, normalizers, stables, for horses, stabilizers, and kernels. Okay, centralizers, the centralizer of a subset or of an individual element. That's just the stuff that commutes with everything in the subset, or the stuff that commutes with that one element. Normalizers, we're good with conjugation, right? That's all the stuff that when you conjugate by it, you send the subset back to itself, or you send that element back to itself. Now, okay, what's fun and exciting about this? Now we're comfortable. This is flash forward a little bit, but with the idea of a normal subgroup. So a subset is normal in its normalizer, right? We can sort of connect all of these ideas. Stabilizers and kernels relate to group actions, and the stabilizer is about all of the elements that act on a given element S and send S to itself. That's the stabilizer of that element S. The kernel is everything that gets sent to the identity, or everything that acts trivially. Next, we adventured into the land of cyclic groups and cyclic subgroups, right? So these are groups or subgroups generated by a single element. That's maybe a group G that is just generated by X. We talked, what did we talk about? We talked about how cyclic groups are unique up to isomorphism of a given order. There's only one cyclic group of each order. We talked about finding different generators, right? The order of an element in a cyclic group and which different elements will generate the group. Infinite cyclic groups. Yeah, all kinds of fun stuff. We extended that idea into subgroups generated by subsets of the group. So we could think maybe our group G is just generated by two elements, or maybe G is generated by a whole subset of elements. That means every element in G can be written as a finite product of elements in your set of generators. So we're sort of connecting the idea of generators and relations and thinking just sort of fundamentally, what does it mean to be generated by a subset? And one big idea for sort of organizing all of our thought processes on subgroups is the idea of a lattice of subgroups. So we use this sort of diagram, this graph, to show the relationships, the containments between the different subgroups of a group. Before we process all our vocabulary, let's hit some of the key results here that actually extend well beyond the context of cyclic groups exclusively. The first really nice one is that if X is an element of order n, then X to the 8th power has order n divided by the GCD of n and a. So we know right off the bat how to find the order of a power of an element whose order we know. Now back to cyclic groups context, right? What does that tell us? That tells us that if you have a generator for your cyclic group, then and it's X, then X to the A also generates your group if and only if A is relatively prime to the order of that element or the order of your group. We also know that for each divisor of the order of our group, there is a unique cyclic subgroup of order D generated by X to the N over D. Okay, so take a second, run through an example of this or find a problem like this from your homework, right? We have a lot we can say based on divisibility, about orders of groups, about generators for groups, about properties of cyclic groups and cyclic subgroups. All right, y'all, let's make sense of some of this vocab. First, the trivial subgroup. That's right, if you just put the identity in your subset, that's a subgroup already. Woo! Let's see, the subgroup criterion, we wrote that one out above. That's just kind of our shortcut, right, for checking that a subset is in fact a subgroup. Let's see, details on things like the centralizer, the center, the normalizer, the stabilizer. We talked through some of those above. Remember, the center is everything that commutes with every other element in the group. Stabilizers and kernels, those are examples of subgroups that come out of group actions. Let's see, conjugation. Oh yeah, it made this list too. I know it was on the first list. It's still important. Let's see, the idea of generated by, what it means to say, oh, every element in this group can be written as a finite product of elements from this subset. All sorts of applications of Bézou's identity. That's actually conveniently everything spelled out below here, right? We could show all kinds of cool properties by saying, okay, if this is the GCD, we get this linear combination of these two elements. What does that allow us to prove about properties of our groups? The beautiful theorem about how cyclic groups are unique up to isomorphism. Let's see, we showed that the intersection of two subgroups is itself a subgroup, and in fact that the intersection of arbitrarily many subgroups is still a subgroup. And the idea of a group being finitely generated, that is, that there is some set of elements, some finite set of elements that generates the whole group. All right, y'all. I think we are now ready to tackle the pinnacle of our group theory knowledge, where we put it all together. We're thinking about quotient groups and homomorphisms. So this is where our subgroup knowledge and our group knowledge together are going to let us form cosets, and from those sets of cosets, brand new groups. Everything comes together in this last chapter. All right, so when we look at this first section, definitions and examples, what definitions do we mean? Well, the big thing is defining cosets, defining quotient groups, defining what it means for a subgroup to be normal. These are our building blocks for all the results that come. Section 3.2 is a very specific, more on cosets and Lagrange's theorem. So this is more examples, more sort of deep dive into the structure of quotient groups, and now what does Lagrange's theorem tell us in this context, or how can we prove Lagrange's theorem using what we know about cosets? One of the big ways we think about Lagrange's theorem in this context is thinking about the index of a subgroup H in a group G is the order of G divided by the order of H. Okay, and then finally, the isomorphism theorems. Really, if there's one that you're going to commit to memory, that you're going to carry with you day in and day out, it's the first one. The first isomorphism theorem is the tool that we use to prove all the rest of them. It's sort of our fundamental key insight on the structure of quotient groups. All right, y'all, let's see how we can do telling the story, putting together the narrative of quotient groups. So where we start is with cosets. Now, if you're going to compute a set of cosets, we need to have our context right. We're talking about cosets of a subgroup within a given group. You got to specify all of those ingredients in order for this to be sort of a well-defined operation. So to take a coset of a given subgroup, pick an element in your group, and then multiply that element by each and every element in that subgroup. Now you've got the coset generated by or represented by that first element G that you picked up. So we can do this for every element in our group. Each one, pull it out, make a coset. A question arises. Are all of those cosets distinct? If you remember, long ago and far away, we computed some examples and saw, oh, no, they're definitely not all distinct. We have overlap between our cosets. So it turns out we have, in fact, more strongly than just some overlap. If two cosets share an element in common, they share every element in common. Otherwise, they're completely distinct. So this is what allows us to put a group structure on a set of cosets, is to say, okay, sort of every element in my group G that shares this coset, we'll just sort of collapse those into a single element. And every single element outside of that coset, we'll find whatever cosets they belong to and collapse those to individual elements. All right. So what we see in this sort of blobby picture is the idea that we can partition our group according to cosets, and then that allows us to have this sort of group structure that's well defined in some way if our in the quotient group, if the subgroup we started with is a normal subgroup. We have a whole host of different definitions for what it means to be normal, all of them equivalent. The basic one is that conjugation by any element in G returns your subgroup to itself. Okay? If the normalizer in your group is the whole group, then your subgroup is normal, and that's what it takes for this operation on cosets, this set of cosets, to form a group. Now wait a second, you might be thinking, what operation on cosets? We've just talked about how we can collapse group elements into cosets, but now how we operate on them, how do we put a group structure on this? Well, our recipe for sort of inheriting an operation on cosets is to say, okay, perform the group operation on two representatives of different cosets. The result now is the coset represented by that product of our two elements. Okay. Y'all, as always, there is, just so much more we could keep saying about quotient groups. So a few more ideas to sort of wrap this up. Okay. One, instead of developing this whole framework thinking about arbitrary cosets, we can base the whole theory on homomorphisms. Specifically, we proved in class that a subgroup is normal if and only if it is the kernel of some homomorphism. This is where that vocab word of fibers comes in. The kernel is just the fiber over the identity, right? Fiber is just a weird mathy way to say all of the elements that get sent to this specified output. We can then set up all of our cosets as fibers over the different elements in our target space. Now, we didn't use that framing in class. I don't expect you to use that framing here. It's just sort of a passing thing to be aware of. One sort of the flip side of this that we did spend some time with was the idea of the natural projection. So the natural projection is the special homomorphism that we're going to cook up so that all of our fibers are cosets and the kernel is this normal subgroup, and all of this sort of by definition or by construction. Skimming through the rest of the vocab here, let's see. We've talked about the idea of conjugation many times. In the context of coset math, right, we need to check that our operations or our maps are well defined. If the input is a coset, right, every coset has many representatives, so we always need to check if I choose a different representative of my coset, do I still get the same answer? Let's see. Lagrange's theorem and the idea of index we've talked about. Cauchy's theorem is a great consequence of this that speaks to life outside of quotient groups, right? Cauchy's theorem says for every prime dividing the order of the group, there exists an element of that order. Woo! Let's see, the first isomorphism theorem is spelled out above with our little space friend. And in fact, all of these isomorphism theorems, I'm going to direct you toward the previous video that I made talking through those. Long story short, they describe the relationships between quotient groups and the way that normal subgroups interact with normal subgroups. And those are some of our big tools for proving things about quotient groups. I would encourage you to really feel ready with the first isomorphism theorem to say, oh yeah, I got this. I can use this. I am ready. All right, folks, I think that's it. If you made it all the way to the end of this long talking through an entire semester's worth, okay, it's only half a semester, but still, worth of fun, bless you. You're amazing. Happy studying. Good luck.